Okay, let's make a start. Before we jump into today's lecture, I have a few announcements. The first is that to remind you that the first assignment, which is about earthquake preparedness, is due this coming Thursday. As with all assignments, the due date is either on a Tuesday or a Thursday. The due date is listed on the syllabus. You can either hand your homework in at the end of the class. We'll have a table up here, and you can hand it in. Or the deadline is always 5 p.m. And if you're not handing it in class, then you need to go and put it in the mailboxes, which are in 340 Macone Hall. And you will find that there is one mailbox for each of the 3 GSIs. So as I've mentioned multiple times, you've all now been assigned a GSI. So that GSI will be grading all of your work. And so you will always need to put on the top of everything that you hand in 2 names. One is obviously your own, and the other is your GSI's name. And then you need to hand it in. You need to put it in the right mailbox for your GSI. Okay? When you go into 340, you'll see all of the mailboxes in front of you, and all of the regular-looking mailboxes are the department mailboxes. The GSI mailboxes, are they on the left or on the right? Left? Left, okay. They're on the left-hand side. So when you look at the stack of mailboxes on the wall, the GSI mailboxes are on the left-hand side, and there's one for Avinash, one for William, one for Cheng. Okay? So the deadline is Thursday, it's 5 p.m. If you're handing in at 5 p.m., you need to put it in the mailbox. It really is a 5 p.m. deadline because the department locks that office at 5 p.m. Okay? So once it's locked, obviously you can't get in, and you've missed the deadline. Okay? I encourage you to bring it in and just hand it in class. That's obviously a very easy way of doing it. Okay? If you have any questions about the format of the assignment, questions like that, the best thing to do is ask your GSI because it's him that's going to be grading it. All right? Any questions about the assignment? No? All right, that's easy. Okay, the second announcement is that our first field trip is this coming weekend. So I talked about this at the beginning of the class. We have 2 field trips. The one this weekend is a tour of the Hayward Fault. The field trip itself takes about 2 to 2.5 hours. Okay, so you need to allow 2 to 2.5 hours for the field trip. We will be walking. We just walk from campus. Let me back up. There are a total of 10 time slots for the field trip on the Friday, this coming Friday, Saturday, Sunday, and Monday. So you need to go to BSpace and you need to sign up for one of those 10 time slots. I believe they're now up. You can see exactly when the time slots are. Okay, so you need to go to BSpace, you need to sign up for a time slot, and then you need to show up for the time slot. 50% of your grade is based on your attendance on the field trip, okay? And the other 50% of the grade is based on the field trip write-up that you do after the field trip, okay? So go to BSpace, sign up for a time slot. Now, once you sign up for a time slot, you will meet the person leading your field trip at the north gate of campus. This is the north gate of campus. So this is Hearst Avenue. This is Euclid Avenue. We're here right now in Stanley Hall, Mining Circle. You kind of go through here, around Macone. This is the library. This is Memorial Glade. Up the hill from Memorial Glade, north gate of campus. Okay? We will leave the north gate of campus at 9 o'clock. Not at 9:10 or whatever time your trip is, not at 10 past the hour. We will leave on the hour. Okay? So when you sign up, make sure you can be there on the hour for the time slot that you sign up for, because otherwise we'll be gone, and obviously you won't know where we've gone. Okay? Can we still get to Hamilton Gulch? We can, right? Just we can't get out, and we come out the same way. Okay, so just so you know, the field trip will be working our way along the Hayward Fault. We'll go through Memorial Stadium, look at Memorial Stadium, which is on the fault, and then we'll go down Hamilton Gulch, which is kind of a little dirt creek that's just behind Memorial Stadium. So bring some shoes that you don't mind getting muddy. Not that there's any mud. Don't come in high heels. You'll need a notebook and a pen, and that's it. Okay? Any questions? Where do we end? We'll end, so the reason I'm hesitating is they're going to put up new fences, most inconvenient, and so I'm not entirely sure how we get out from Hamilton Gulch. We will discover that on the first field trip. But the field trip basically will end over somewhere between Memorial Stadium and the Clark Kerr campus. So if you then have something else that's back on campus, you're going to need sort of 20 minutes to walk back to the campus. You should allow about 2.5 hours. So really you need a 3-hour time window. The field trip will not last 3 hours. Yeah? So the question was, do you need to include photos to get full credit? Adding photos to show what you're talking about will certainly help. Any other questions? Yeah. Okay, so when you look on BSpace, you can see who. Let me see, sorry. Okay, so you can see who is leading. Basically, you can see a GSI, a name assigned with each of the field trips. That's the GSI that will be leading the field trip. Okay, you do not have to sign up for the field trip that's with your GSI. I mean, if you can, it makes sense. Get to know him. It can only help you during the course of the class to know your GSI. So if you can go on a field trip that's been run by your GSI, that would be great. But that's not a requirement. Any other questions? Yeah. No. Yeah, no. We're not going to walk back in a single file line. Yeah. Any other questions? Did I hear somebody? No. Okay. So do sign up, particularly if you have limited schedule availability, sign up sooner rather than later. There's a maximum of 30 slots on each of those 10 field trips. So if you're not available for the duration of the weekend, you need to sign up quick. Okay, all right, last announcement, or logistical thing, I guess. Several of you have come to me to ask about my recommendations for good study skills. So here are my comments on good study skills. The most important thing here is to be active. That's why I encourage you to come to the lectures, engage with me, ask me questions, and be active, an active participant in the lectures. That's the most effective way to learn the material. I encourage you to write notes. You can see, I hate to say this, but I think I might be dating myself by my comment here. Scribble all over the lecture slides. How many people actually have a paper copy of the lecture slides? Oh, 1, 2. Excellent. 3. Oh, I'm not completely. So, okay, clearly most of you are not printing out copies of the lecture slides. So how are you writing down notes? How are you making notes? On top of the slides, okay. Oh, we have somebody annotating a slide here. Okay, what else? In a notebook? What else? In a Word document? Anything else? This is a genuine question. Good old-fashioned piece of paper? Anything else? I mean, the point is that you have multiple options. It doesn't matter which one you use. You need to figure out, those of you who are freshmen, hopefully those of you who are beyond your freshman year have figured this out. You need to figure out what works for you, okay? I can tell you that what works for me is to physically scribble on the lecture notes, okay? And so writing down notes on top of the slides, that's what works for me. You have to figure out what works for you. It does require some effort, and that's the whole point. Putting in the effort will help you learn the material. Okay, reading, as I described at the beginning of the class, the reading in the textbook is not, this class is not, I'm not teaching you a textbook, okay, which I like to think is a good thing. The textbook that you have covers much the same material, but in a very different approach, with a very different kind of take. So I'm assigning you reading. This was reading specifically for today's lecture, actually. I encourage you to do the reading. I encourage you to do the reading before the lecture. You'll be much more familiar with the material, and then you'll be ready to ask questions. So do the reading, and doing it before the lecture is definitely a good thing. And then, of course, it's very important to then review your notes. If you can, I know it's difficult to do this, but going through and reviewing your notes from a lecture a day or two later will really help you internalize the material. I guarantee it. So, of course, most people will just put them on the shelf, file them away, and get them out when the lecture arrives. I really encourage you to spend an hour reviewing your notes a couple of days after a lecture, and that way you will remember much more of the material. Okay? So you have to try various things, and you have to figure out what works for you, and then you have to put in the effort. It's that simple. So hopefully that answers those of you who asked me this question, my suggestions on study skills. That's my comment. Any questions or comments on this? All right. How many of you do actually have the lecture notes in front of you? Now I'm just interested. Okay, maybe about, I don't know, less than a quarter or a fifth. Okay. All right, let's get to today's material. So we're going to start talking about faults. The field trip at the weekend is to walk along the Hayward Fault, so we'll be looking at the Hayward Fault specifically. Today I'm going to talk about, in general sense, about faults, and then on Thursday we will talk specifically about the Hayward Fault in sort of preparation for the field trip starting on Friday. And so the reading is Vault Chapter 3, which talks about faults. Okay, so the first question is, what is a fault? Anybody? Yeah. Okay, so it's the... Say again? What do you mean don't meet? Oh, I see. Okay, so it's the place where two continental plates meet. Okay, that's right. And so when we're out in the field as a geologist, what do we actually expect to see? A crack, right? A crack in the ground. And how would we identify a crack? I mean, I'm thinking about in a natural environment, not on a paved street. Yeah. A cliff, some kind of cliff. Okay, that's right. So essentially, what all of the fault is it is a fracture through the Earth's crust. Okay, the Earth's crust being the rock. Okay, and this isn't a great photo, I know, but this is one of the most beautiful examples of faulting, where you can see it on a very local scale. This is the Corinth Canal in Greece. And Greece is undergoing some extensional faulting. And so what you can see here, so how many of you know what I mean when I talk about sedimentary layers, sedimentary beds? I think you've all covered this in high school. In fact, I know you have. So those of you who didn't put your hand up, shame on you. So sedimentary layers are these horizontal layers. One way that you can lay down rock is you lay down sediments. Okay? They get buried, and over time they solidify and form sedimentary rock. And in that situation, the layers that are laid down, they're laid down due to gravitational processes, typically underwater, and so they form these horizontal layers. And so I know it's difficult to see, but hopefully you can see these horizontal layers that are shown very nicely in the margins of the Corinth Canal here. So these are the horizontal layers. But then if you sort of look down here, you can see that obviously there's these nice continuous horizontal layers, but then they are broken right here. Okay? And then you can see more horizontal layers here, and then they're broken again right here. Sort of difficult to see further on. And so this is my little sketch of what we're seeing when we look at the wall of this cliff. Okay? So these are the horizontal layers. They're broken. See the same horizontal layers. They're broken, and then the same horizontal layers. And these horizontal layers are offset across these breaks, these fractures. Okay? So these, of course, are the faults. And so this is a fracture that runs through the rock and allows the blocks on either side of this fault to move with respect to one another. Okay? And of course, this is different. This is a vertical fault. We often think about the San Andreas fault, which many people think of as a horizontal fault, and we'll come to that in a minute. This is a vertical fault, and motion on this fault has caused these two blocks to separate. So what is the relative motion on this fault? Can somebody describe it for me? Yeah. Interesting. So tell us why you think it's right lateral. Okay, so if you're standing here and you're looking along the lines. Okay, you're looking here. Okay, looking this way, and it went to the right. Okay, so what you just described is exactly the right way of describing it. The only catch is that this isn't a strike slip fault. So let's not talk about the fact that this is a right lateral fault. Let's talk about the fact that if you stand here and you look along towards the fault, you can see that this side has gone down. So this fault is vertical, nearly vertical, so you can see that this block has gone down relative to this block, which has gone up. Of course, all we can say is what's the relative motion across this fault. So this has gone down, and this has gone up. Okay, so you can see that from the offset of the layers. So it's about looking at how, in this case, the sedimentary layers or some other kind of marker on the two sides of the fault have moved with respect to one another. Okay. So in this case, so here's the arrows actually drawn on the walls of the canal. This side has gone up relative to this side, which has gone down. Okay. So the next question is, well, that's great, that's a fault, but do I care about it? Should I be worried about it? And if we're only worried about the hazard that a fault poses, if that fault is active, right? There can be faults everywhere, but if they're not active, if there's no likelihood that there's going to be motion on this fault, then there really isn't any hazard associated with it. It's only when the fault actually moves that we have an earthquake and that there's hazard. So the second part, now having identified a fault, now we know how to identify a fault, is answering the question of whether it's still active. Okay? So here's a picture. This is a different scenario. This is in California, and obviously this is a photograph of a field. So is this an active fault? Sure, absolutely it's active. These are obviously just plowed. This is a plowed field, right? So it's been plowed no more than a few months before the picture was taken, and clearly these mounds have now been offset, so this is most definitely an active fault. Okay? When we describe the motion on this fault, what's the motion on the fault? I heard somebody say left lateral. That's right. So this left lateral and right lateral terms, I'm glad that you guys have obviously been doing the reading. Left lateral and right lateral terms, those are used specifically for strike slip faults. Okay? And we'll talk about this in much more detail, but since you're using the term, strike slip faults are faults where the two pieces of rock slide horizontally past one another. Okay? So this picture here is a strike slip fault because this block here has moved this way and this block here has moved this way in a horizontal direction. There's very little vertical motion across the fault. So this is a strike slip fault, and as several of you just said, this is a left lateral strike slip fault. And it's left lateral because if you stand here and you look to the other side has moved to the left. Yeah. So the question is, what if you're standing on the other side? So everybody look at the picture. Imagine that you're standing on the other side. I hear people wanting to answer. Just wait a moment. Everybody stand on the other side. Imagine you're standing on the other side, looking back towards us. What do you see? It also moved to the left. Okay? So it doesn't matter which side of the fault you're standing on. If you stand here and you look this way, it's moved to the left. If you stand over here and you look this way, this block has moved to the left. So there's no ambiguity. Okay? Everybody see that? It's going to be key. All right. So yeah, so this is a left lateral strike slip fault. What about this one? What's the motion? Just describe it. Somebody describe it. Say again? A dip. It has a dip, that's right. We'll talk about what the term dip means in a minute if you don't know what that means, but this interface, the fault here, does have a dip, that's true. Say again? Vertical. There's been vertical motion here, right? So we don't apply this left lateral, right lateral term here because the motion here is that the relative motion of these two blocks is in the vertical direction. This block has clearly moved up relative to this block, which has moved down, okay? So we don't talk about this as being left lateral or right lateral. I'll tell you how we describe it in a few minutes. But this block clearly has moved up and this block has moved down. Is this an active fault? No? Why not? So she says no, and the reason is that it just looks like it's been like that for a long time. Okay? Anybody else want to add anything? Well, first of all, the question is, what does it mean to be active? So we obviously, for it to be active means that there's some likelihood that it's going to move in the future. And what we usually mean is that, that usually means is that we have evidence that it's moved recently. If it's moved in the recent past, it's likely to move again. Okay? And so what does it mean for it to move in the recent past? So does that mean it has to have moved in the last month? Well, if it had to have moved in the last month, then we wouldn't be worried about the Hayward fault, right? Obviously, the Hayward fault has not moved in the last month. When was the last time that the Hayward fault moved? Nobody knows? Yeah. Close? 1868. Okay? So the last big earthquake on the Hayward fault was in 1868. Okay? So clearly that's recent enough that we're worried about it. Okay, so that's the motion. We actually can't tell if this is active or not. There's no data here to tell us whether this fault last moved a month ago. Probably not, because it's clearly, they've cut through it. There's no evidence that it's moved since this cut was made. I don't know if this is a road cut, probably a road cut. But we have no idea whether this moved, 3 million years ago or 10,000 years ago, so we don't know if that's active. So when it comes to defining what do we mean by active, this is actually done by legislation in California. And so what we've done in California and Nevada is that we've mapped all of the known faults in California, and then we've estimated the last time that they slipped. Okay? So the red earthquakes are what's called historic, as in we actually have records of fault motion on these faults. And so the San Andreas fault, all the way from Mendocino Triple Junction, all the way down to the Mexican border, is a historic fault. The northern section ruptured in 1906, and the southern section ruptured in 1857. Okay? The Hayward fault, I talked about the Hayward fault rupturing in 1868. It's difficult to see on this map, I know, but that's this little red section here. Okay? And then the ones that in sort of the last 10,000 years or so have ruptured are shown in yellow, and getting older goes to purple and blue. Okay? So we actually have a legislation here in California that defines what we consider to be an active fault. An active fault, it means something that's had slip on it in the last 11,000 years. So there are official maps. This is one of these official maps. This is Berkeley campus. This is the Memorial Stadium. And this is the Hayward fault. And these are what's known as the Alquist-Priolo earthquake fault zones. So legislation, I'm now blank forgetting what year this legislation was introduced, but this legislation says that, and it defines an active fault as one that we know to have ruptured within the last 11,000 years. And then these fault zones are defined as a region that's within 50 feet of a mapped fault. And there are special rules about building in Alquist-Priolo earthquake fault zones. So we now have to define in a very specific sense, a legal sense, what is in a Alquist-Priolo earthquake fault zone, because then there are laws about what you have to do if you want to build in that zone. You have to do a special type of study. Essentially, you have to show that you are not building on the fault. Okay? That's essentially what this legislation says. As you can see, this swath is actually within these zones, and so when the university was going through the process of building the new sports facility that wraps around the stadium and then the new stadium, they had to go through this special process in order to be allowed to build in this zone because it's in this earthquake fault zone. All right? And so the university did, to its credit, go and completely rebuild the stadium. So this is a photograph sort of partway through the construction. They essentially, the only piece of the stadium that remained was this very outer wall that you can see here. The outer wall of the original stadium built in 1923 was left intact. And then they completely hollowed out the interior, and then they completely rebuilt the stadium inside that old external wall to the stadium that we have today. In fact, they put special design. This stadium is built in sections. The idea that when the Hayward fault ruptures, the fault pretty much runs goalpost to goalpost, that the various blocks of this stadium will move with respect to one another. Sounds like fun. We will talk about this in great detail on the field trip. We'll actually go into the stadium as part of the field trip. Okay? All right, so when we look at the known faults in the Bay Area, this is what they look like. The San Gregorio fault is mostly offshore, just clips the peninsula here. San Gregorio fault, of course, the San Andreas fault. The Calaveras fault splits off the San Andreas fault, and the Calaveras fault then splits into the Hayward fault, which continues onto the Rogers Creek fault, and then also the Concord Green Valley fault. And then the Greenville fault is further to the east. And so these are the primary faults that have been mapped out and we know about in the Bay Area. Yeah. Every single one of them is a right lateral strike slip fault. That's right. And so across California, the relative motions of the tectonic plates across California, the Pacific plate over here is moving in this direction relative to the North American plate that's moving in this direction. Okay? So if you stand over here and you look in this direction, the North American plate is moving to the right. So the relative motion of these two tectonic plates is this sort of right lateral strike slip motion. And so all of these faults are right lateral strike slip faults that are accommodating the motion between the North American plate and the Pacific plate. Yeah.